Hey guys, Mr. Betts here. In topic 6.2, we looked at something called Riemann sums, which is something that we're going to be able to use to approximate the area between a curve and the x-axis. And a Riemann sum is something that we can generalize to the point where we can use it to, instead of approximate, find the exact area under certain curves. So let's take a look a little bit deeper here. So a Riemann sum is a sum of geometric shapes. We are typically going to use rectangles, but we'll also see trapezoids. And the sum of the shapes, the sum of the areas of the shapes, is going to approximate the value of a definite integral. So if you remember, if we are evaluating a definite integral, and I'm going to use a and b here because those are our limits on the integral, that integral represents the area between the x-axis and the curve between x equals a and x equals b. Well, a Riemann sum is going to be a geometric area approximation for that integral. And the idea is we're going to break it up into subintervals. And for now, I'm trying to make it obvious that those subintervals do not need to be the same width. They can be. And then on each subinterval, we're going to pick the value of the function at some point. It really doesn't matter where. Okay, so I'm being super general at this point. But if I pick the value of the function at any point on each of these subintervals and use that as the height of a rectangle, and the width of the rectangle, I'm using just the width of each subinterval, then the areas of these rectangles added together is going to be an approximation of the value of the integral, which is the area between the curve and the x-axis. So this sum, the sum of these areas, is what's called a Riemann sum. And the idea here is this f of x is the height of the function at some point, so that's going to be the height of the rectangle. The delta x sub I is the width of each subinterval. So for example, on our third subinterval right here, this is delta x sub, say, 3. If this one right here is delta x sub 1. Sometimes you'll see the subscript start at 0 and count up from there, but the idea is basically we're just taking the height of a rectangle times the width of a rectangle, and then we're adding a bunch of those together, in this case n of them. So in the picture I have here, n would be 5. So in the most general sense, it doesn't really matter how many rectangles we use. It doesn't matter where along each subinterval we choose to use the height of the function. It doesn't matter if the widths of the subintervals are the same. All of these cases are still going to be called a Riemann sum. Now, for our purposes, we want to be able to generalize. And in order to generalize, we're going to kind of formalize some of those things. So when we can, if we're given a function, there's certain things that we're going to do. So one of those things is to simplify things for us. Rather than using different widths, we're usually going to use the same width. Okay, so depending on how the function is presented to us, we may or may not be able to do this. If the function is presented analytically, then we can find the height of the function at any point. So one thing we're going to do is we're going to say, okay, if there's going to be n subintervals, and they're going to be equal width, then what we can do is we can figure out the width of each subinterval, which we're going to call delta x, by finding the width of the entire thing. So that width right there is going to be b minus a. And then if we want to divide it into n equal subintervals, we're going to take the width of the entire interval and divide it by n. And so that's going to give us the width of each subinterval. So this width right here is going to be delta x. And then the x values here are going to be a plus delta x. And then the next one's going to be a plus 2 delta x. And then the next one's going to be a plus 3 delta x. So essentially what we're doing here is we're adding delta x over and over again, and eventually this is going to be, the last one here is going to be a plus n times delta x. So if we're using n subintervals, if we add delta x n times, then we're going to get to the endpoint. So b is going to be the same thing as a plus n delta x. Another thing that we're going to do to generalize this is we are going to use the same, we're going to be consistent about where we find the height of the function. So we've seen in the last topic, we've seen approximation methods like LRAM, which stands for left rectangular approximation method, RRAM, right rectangular approximation method, MRAM, midpoint rectangular approximation method. And the idea is, rather than just picking any point anywhere along some subinterval, if we're doing LRAM, we're always going to use the height at the left endpoint. Okay, so we're going to get a picture that looks like this. If we're doing, on the other hand, RRAM, then we're always going to use the value of the function at the right endpoint. So we're going to get heights given at the right endpoint of each subinterval. If we do MRAM, then we're going to be using the height halfway in between. By generalizing this, what it's going to allow us to do is come up with a formula, and that formula we're going to be able to use and plug in different variables rather than having to essentially do this brute force for each particular problem. Okay, so if I kind of go through the process here, I'm going to show how we would do this with RRAM, with right rectangular approximation method, which is what I've started drawing here. And then we'll kind of look at the other formulas that we get with LRAM and MRAM, although RRAM is going to be the one that we use the most often because it is the easiest of the formulas to work with. So I'm going to start with just kind of writing out all of the terms that we're going to add together. And so the area of the first rectangle, okay, I'm going to just call that A sub 1. So the area of that rectangle, the width of the rectangle is delta x, and then the height of the rectangle is going to be f of A plus delta x. So that's the area of the first rectangle. Then the second rectangle, the width is going to be delta x again. And remember, this was A plus 2 delta x. So the height of the function then is going to be f of A plus 2 delta x. And then we're going to have delta x plus f of A plus 3 delta x. I'm sorry, that should be times in there. And so on. And that's going to go all the way till we get to the very last rectangle here, which is also going to have a width of delta x. And the height is going to be f of b. But remember, f of b is the same thing as f of a plus n delta x. And I want to write it that way so that where we are evaluating the function is in the same form for all of these. So what I can do now is a couple of things algebraically. One is I can factor out that delta x. So this is, let me identify this here. This is RRAM n. So right rectangular approximation method with n rectangles. So we can factor out a delta x, and what's left is a f of a plus delta x plus f of a plus 2 delta x plus f of a plus 3 delta x, and so on, all the way up to f of a plus n delta x. Now, this expression right here, notice that each of the terms, and I forgot a parentheses there, each of the terms is in the exact same form, except the number that we're multiplying by delta x is just increasing by 1. So the next one's 3 delta x, next one's 4 delta x, all the way up to n delta x. So this is a really good candidate for what's called sigma notation. So in sigma notation, we're going to have the delta x out front. So we're going to take the sum of f of a plus I delta x. So I'm replacing the numbers that I have circled here with an I. And I starts out at 1, and it goes up to n. So in a closed sigma notation form, if we're using equal width subintervals and we're using RRAM, then the approximation we're going to get is going to be given by this formula. Now, I mentioned this already, but I want to say it again. By coming up with a formula like this, we can be very general and plug in values for variables and evaluate this very quickly. Your calculator has the capability of evaluating a sum in sigma notation, but this is also something that with certain sums, we can evaluate it algebraically for any particular n value. So I want to look at this formula here. This is the formula for RRAM. Like I said, we're going to use this one the most because it is the easiest of them to work with. So notice again that we have the width of each subinterval is delta x. Remember, delta x we get by doing b minus a over n. And then f of a plus I delta x is going to give us the height of each of the rectangles. So what we have here is a sum that's doing a width times a height n times, and so we have n rectangles that we're getting the areas of and adding together, and that sigma there means that we're adding. In a similar fashion, we can also come up with formulas for LRAM and MRAM. Notice that I have two different formulas for each of those. One of them is if we start I at 0, and the other one is if we start I at 1. You will see both of these forms pop up, so it is good to at least be exposed to them. But essentially, what's happening here with LRAM is that if I starts out at 0, then the very first one here is going to be f of a. So on the first subinterval, we're evaluating the function at the very left endpoint, where when I was 1 up here, this is f of a plus delta x, which is the right endpoint of the first subinterval. If I is 1, essentially what I did here is I replaced the I here with I minus 1. So this, when I is 1, just becomes a 0. So we end up with the same thing here. The first height is going to be f of a. If you look at the MRAM formula that I've got here, when I starts out at 0, we're going to start by adding half of delta x. So what that does is it starts at the left endpoint and adds half of the interval, evaluates the function there to get the height at the midpoint of the first subinterval. If I starts out at 1, then we subtract 1/2 from I so that we're still doing f of a plus I, or half of delta x. I also want to point out that when when I starts out at 0, we go from 0 to n minus 1. So if you think about counting, normally we count starting at 1 and go to n. That would be n things, n rectangles. So if we were counting starting at 0, if we want to count n rectangles, then we would only go up to n minus 1. So for example, 10 rectangles, if we start at I equals 0, we're going to go 0 through 9, and that would give us 10 rectangles. Okay, so again, some general formulas here that we can use for our Riemann sums. And what we can do here is we can say, okay, if we want to use 3 rectangles with LRAM, we can just plug 3 in for n in the formula here. Remember, a in the integral is the lower limit. B is the upper limit. Also notice that B is not anywhere in these formulas except that we use it to calculate delta x. So we can use a and b to figure out what delta x is, use n to figure out what delta x is, plug in what we know, and then evaluate the sum. So it's a closed form, very generalized, allows us to use these formulas for large values of n if we have a computer or calculator then that can help us evaluate these sums.